Oh, right. So for 57 through 59, we've got this graph below. The graph below shows the relationship between speed and elapsed time for a car moving in a straight line. Um, 57 determine the magnitude of the acceleration of the car. So you maybe remember this memory trick that we showed you earlier on the year, DVA. As you move to the right along this DVA little trick, you're taking the slope. And if you move to the left, you're taking the area. So in this case, let's talk about what type of graph we have. We have a speed graph, and we want the acceleration. So for 57, what we can do here is we're at velocity, we have a speed graph, and we want the acceleration. We're going to the right. We'll take the slope of the graph. So slope is change in y over change in x. Now let's pick a couple of data points here. Nice easy one to use is the 0, 0 point here. And then another easy one to use here would be the 8, 10 point up here. So the change in y from 0 to 10 will be 10 meters per second. And the change in x from 0 to 8 will be 8 seconds. 10 divided by 8 gives you a value of 1.25 meters per second squared. Box that, use that to your answer. Now you could have gotten the same answer by doing acceleration is change in velocity over time. Notice that the change in velocity would be the same. It goes from 0 to 10, and the time would also be the same, from 0 seconds to 8 seconds. And so both ways you'll get the same answer and full credit. Now, let's look at 58, 59. For this one, now we're going the other way here. We want to calculate the total distance traveled by the car during the time from 4 to 8 seconds. Now, looking back at our memory trick here, we're at velocity, so we have a velocity graph, and we're calculating the distance here. So we're going to the left along our little memory trick here, so we're taking the area. Well, what exactly are we taking the area of? Well, we're taking the area of the space under the graph from 4 seconds to 8 seconds. So, 4 seconds, 8 seconds from here to here. This is our line, and the area we're taking is this trapezoid, which I've just drawn out. So, the next way of breaking this one up is to break the trapezoid into a triangle and a rectangle. We can take the area of this rectangle at the bottom here, take the area of the triangle towards the top, and combine them to get the total area of our trapezoid. So I'm going to start with the rectangle at the bottom. Now the area of rectangle is length times width. Don't forget to show your equation. This is a part 2 question. You need to show your equation to get full credit. And when we plug in for our length and width, for our length I've got 4 seconds along the bottom. And for a width I've got 5 seconds going along the y-axis. It's worth pointing out here that we showed our equation and we substituted with units here. Length and width have units. Ooh, I'm sorry. The speed is going to be 5 meters per second. And notice that the seconds now cancel out. Now we're left with meters, which is what we're looking for. So we plugged in, we've shown all the work. 4 times 5 is 20 meters, and we're good. So we've got the area of our rectangle towards the bottom. Now let's calculate the area of our triangle at the top. The area of the triangle is, again, show our equation, 1/2 base times height. And when you plug in 1/2 for the base, I'm going from 4 to 8 seconds, so our base is going to be 4 seconds. And our height, I've got the height going from 5 meters per second to 10 meters per second. From 5 to 10, that's a height of 5 meters per second. 1/2 times 4 times 5 gives you a total of 10 meters. Notice the seconds cancels out again. So we're left with the unit of meters, which is good. That's what we're looking for. Now we've calculated the area of the rectangle at the bottom, the triangle on the top. So to get the total area traveled during this time, we can just combine the two areas. The 20 meters plus the 10 meters gives you a total of 30 meters, and that will be your answer.